Hello, welcome back to Lecture 35 in Fundamentals of Inorganic Glasses. This is the final lecture of the course, and we are going to finish with a discussion of fiber optic communication systems. This comes from the chapter on optical properties, which is chapter 19 in the book. So fiber optics are useful for a wide range of applications. Today, we're going to focus on optical communication systems because the world is connected by these very thin strands of high purity glass, about 125 microns thick, or about the same thickness as that of a human hair. And we use these very thin strands of glass fibers to communicate very high bandwidths of information at the speed of light across continents and across the oceans. The invention of fiber optics is really what brought us into the information age. So we're going to focus this lecture on some of the science about what makes fiber optics possible and what are some of the concerns that we need to address with fiber optic communication systems. But I also want to point out that fiber optics are used for sensor applications because the refractive index is sensitive to strain and temperature and pressure. They can be used as very accurate sensors for any of these variables. Fiber optics are also ubiquitous now in medical applications. They're used in endoscopy, so doctors can see inside the human body while only passing a very thin fiber inside. They're also used for high-intensity laser light delivery, so they can be used to help blast little localized regions within the body for surgical applications where the body doesn't need to be really opened up. And so fiber optics has been transformational in the field of medicine, just as it has in the field of telecommunications. And fiber optics can also be used for illumination because of the ability to propagate light. Now, the basic governing equation for that governs refraction and therefore governs the optics of fiber is Snell's law. Snell's law relates the angle of refraction here, theta 2, to the angle of incidence, theta 1, for a ray of light that is passing from one medium that has a refractive index of n1 into another medium that has a refractive index of n2. And the angle of the light changes as the refractive index changes, and that change of the angle obeys Snell's law, where the ratio of the sine of the angle of refraction, theta 2, over the sine of the angle of incidence, theta 1, is equal to the ratio of the velocities in those media, and that's inversely related to the ratio of the refractive indices, so n1 over n2. So if we consider, what if you have an incident ray of light that is in a higher refractive index medium passing into a medium with a lower refractive index? For example, what if you have an incident ray that is propagating through water and it encounters an interface between water and air? Air has a lower refractive index than water, and therefore the light can travel faster in air than it does in water. This causes the refraction angle theta 2 to be greater than the angle of incidence theta 1. So this ray actually changes direction, and that change in direction is governed by the change in angles, which is given by Snell's law. Now imagine if we take this angle of incidence here, theta 1, and we increase it. So we're bending this incident ray of light upward. The refraction angle is going to also become larger until it eventually becomes 90 degrees, at which point the refracted light is propagating along the interface between the water and air. When this happens, the angle of incidence that gives this 90-degree angle of refraction is labeled as theta c. This is the critical angle of incidence, which means that light that is propagated at that angle would follow the interface between the two media. So if you increase the incidence angle so that it is greater than the critical angle, theta 1, this makes it impossible for the light to refract into the next medium because Snell's law simply cannot be satisfied. This results in all of the light reflecting off of the interface because it cannot propagate into that other medium with a lower refractive index. This occurs for all angles of incidence that have an angle greater than the critical angle. So this theta 1 greater than theta c. And as a result, all of the light is reflected at the same angle, and we get what is called total internal reflection, which means that all light signals that propagate at those angles can be contained within the medium of a higher refractive index. And this is the basic principle for how optical fiber works, is that we have a very thin strand of glass that has two different regions in it. There is a core glass, which has a higher refractive index, N1, and then there's a cladding glass that has a lower refractive index, N2. And so for any incident light that comes in at an angle that is greater than the critical angle, that light is going to be completely reflected off of the interface between the core and the cladding. Since the core has a higher refractive index compared to the cladding, it reflects off of that interface and then keeps reflecting off of the interfaces as it propagates down the length of the fiber. And if total internal reflection is satisfied, then the signal flight can keep propagating, and the only absorption that occurs would be due to the scattering loss within the core of the fiber itself. So the primary function of optical fiber is to guide light propagation via this mechanism of total internal reflection. But in order to do this, we need to construct a fiber that has these two regions, that has a core region of higher refractive index and a cladding region of lower refractive index. The usual material of choice for optical fiber is germania-doped silica. So the cladding would have the lower refractive index, which is 100% silica. And since the core needs to have a higher refractive index, that silica gets doped with germania. And the plot on the right shows how the refractive index of the glass increases as you go from pure silica on the left-hand side to pure germania on the right-hand side. There's a linear increase of refractive index as the larger germania is added to silica. And so the core itself is germania-doped silica, and that gives it a higher refractive index compared to the cladding. Now, the main problem that needed to be addressed when optical fiber was first invented was absorption due to water. If we make silica fibers by simply melting quartz, it doesn't work because it doesn't give low enough attenuation for telecommunication because quartz has impurities, and one of those impurities is water. And water absorbs at exactly the same wavelengths that are used for telecommunication, 1310 and 1550 nanometers. And because of these OH absorption peaks, telecommunication fibers would not be possible if they have water contamination. So the key discovery for the invention of low-loss optical fibers was made by Peter Schultz, Don Keck, and Bob Maurer, who are shown here, working at Corning Glass Works back in the late 60s. And the main discovery was made in 1970. And if you go to the Corning Museum of Glass, you can see this page from Don Keck's lab notebook where he calculated for the first time, or he measured for the first time, a loss less than 20 decibels per kilometer, which was the threshold required for the initial telecommunication systems. Here he measured 17 dB per kilometer, the lowest loss that had ever been obtained. And you'll note he famously wrote whoopee on the side of his measurement. And you can see this if you go visit the Corning Glass Museum. The key invention that made this possible was not really a materials invention, but a process invention. And this is outside vapor deposition. With the outside vapor deposition process, the silica is made synthetically, and it's done so in a glove box that is free of water. And the way that this works is that there is a target rod that is rotating, and then there is a flame that is going back and forth along the axial dimension here of the target rod. And being fed into that flame, we have silicon tetrachloride and oxygen gases. The silicon tetrachloride and oxygen react at those high temperatures. They form silica, SaO2, and chlorine gas. The chlorine gas goes through a scrubber that removes the chlorine gas from the exhaust, and the silica forms as a soot that gets deposited onto this target rod. And as the flame goes back and forth, the silica soot gets deposited along the rod, and the rod is rotating so that we have radial symmetry. Now, in the inner part, the core part, we also add germanium tetrachloride, and that germanium tetrachloride reacts with oxygen and it forms germania and chlorine gas. We've got germania in the core to increase the refractive index, and then as we go from the core to the cladding, it ends up being pure silica. The feed of germanium tetrachloride is turned off, and in that way we get a higher refractive index in the core compared to the cladding. Now, when this process is done, what we get is something that looks like on top here. This is soot deposited onto that target rod. And the soot is white because it has a lot of porosity with it. This needs to be brought up to high temperatures. The target rod is drilled out. It's brought up to the preform is brought up to high temperatures where it consolidates, and the consolidated preform is shown on the lower left. You can actually see the core region here in the middle because of the difference of refractive index in the core region compared to the cladding region. The higher germania content of the core causes it to refract differently, and therefore you can see it visibly here. This consolidated preform is fully dense, so all of the porosity has collapsed, and you have a fully dense preform that can then gets tipped up vertically and placed at the top of a fiber draw tower. At the top of the fiber draw tower, the tip of the preform is heated up, and then it is pulled down into fiber. And this gets coated with a polymer on the way down to help provide mechanical protection. And then it gets spooled at the bottom into spools that look like this. So it's kind of like a spool of thread with a sewing machine, but much larger. Each spool can have tens of kilometers of fiber, where the fibers are about 125 microns thick. Now, we don't just have a single fiber that propagates the signal, but a whole bunch of fibers, and they get protected by putting them into cables. Each of the individual cables here is color coded, so we know which fiber is which on both sides, and they get bundled together. And usually, the transoceanic cables are much larger because they've got much more fibers. The transcontinental cables are also quite large, and then if you go to local delivery of the information, they would be much smaller cables. Now, there are different ways to construct the refractive index profiles of optical fiber. In any case, we need to have a higher refractive index core compared to the cladding. If one makes a relatively large core, let's start in the middle here with a multi-mode fiber that is a step index fiber. And with a fiber that is like this, the cross-section is shown on top, where you've got the core in the middle and then the cladding around the outside. The refractive index profile shown in the middle shows that there's a higher refractive index of the core, and then there's a sharp interface between the core and the cladding, and that steps down to a lower refractive index of the cladding. And so this enables light to be propagated through the fiber along various modes, meaning there are different modes of light that are supported here that are propagating at different angles. They all obey total internal reflection. But the problem is because these different propagation modes at different angles experience different distances of propagation because they're bouncing off of the interfaces at different angles, and therefore the total distance of propagation is different. That means that different modes of light take different amounts of time to go from one end of the fiber to the other end. So this is a problem with multi-mode step index fiber. And one of the ways to fix that problem is to go to single mode fiber. With single mode fiber, the core is a lot smaller compared to the cladding, and because of the much smaller dimension, only a single mode of light is supported, and all other modes are lost, and therefore you just have the single mode that propagates through, and that eliminates this intermodal dispersion since there's only one mode. This does make it difficult, though, to splice the fibers and to make sure that the very small cores are aligned with each other. If you have two fibers and want to put them together, It's a very delicate process to make sure that the cores are lined up, and that is especially difficult for single-mode fiber. Another approach is to go to multi-mode gradient index fiber, which is shown on the left. Here, the refractive index profile is not flat in the core, but it has a maximum of germania and therefore a maximum of refractive index in the center of the core. And then as we go from the center of the core towards the cladding, the amount of germania gradually decreases. The amount of, or the refractive index gradually decreases until there's no more germania left, and the refractive index is the same as that of the cladding. Now, with multi-mode gradient index fiber, or GRIN fibers, as they're called, um, the modes that propagate longer distances spend more time near the outer parts of the core, and near the outer parts of the core, this is where the refractive index is lower. And so basically, the longer propagation distances cancel out with an average lower refractive index, and therefore the total propagation time is the same for the different modes. And so this is a clever way to be able to use a larger core, which is easier to splice, but with having this tailored refractive index profile, eliminate the problem of intermodal dispersion. So the world is connected by fiber optics. This shows a picture of some long-haul submarine systems, giant cables that are across the floors of the ocean. You see how they connect the west coast of the Americas with Hawaii and with Australia and New Zealand and East Asia, the connections that go along the Indian Ocean, along, all around the continents here, around Africa and Europe. A lot of transatlantic lines that connect North America and Europe, that connect South America with Africa. Fiber is everywhere. And if you look within the country here, there are terrestrial systems that are buried across the country. And this is what connects the world. This is what enabled the invention of the internet and bringing human society into the information age. It was the invention of these low-loss optical fibers that enable the transmission of enormous bandwidths of information at the speed of light. Closer to home here, there are local networks. Many businesses and schools, the places of employment are connected by fiber. More and more homes are connected by fiber to the home systems as well to get higher bandwidth communication within the home. When we consider a fiber optic communication system, there's not just one signal that propagates, but a large number of signals that propagate at different wavelengths. And each one of these signals has its own central wavelength here, lambda 1, lambda 2, lambda 3. They get combined into a single signal using a multiplexer, which is across many different channels. And so all of these individual signals across individual channels get combined by a multiplexer into a signal that spreads across a much larger bandwidth that has many different channels. That signal propagates for tens of kilometers or hundreds of kilometers. There is loss in the fiber due to Rayleigh scattering. That hasn't been eliminated yet. And so every once in a while, the signal needs to be amplified, and that's done using an erbium-doped fiber amplifier, which is through a stimulated emission of radiation, which I'll show you in a moment. Along the way, channels can be added or dropped as appropriate, and at the end, there's a demultiplexer, which breaks the multi-channel signal into separate individual channels that they can go on to their destinations. This shows you an example of how the signal, the binary signal of zeros and ones, can be encoded optically. This is a non-return to zero signal, or NRZ signal, where if you look at the power of the signal as a function of time, wherever it's zero, that's a 0 bit. So this is a 0, 0, followed by a 1, 1, 0, 1, 0, 1, 1, 1, 1, and so on. So there's a certain power level that is 1, another power level that is 0, and the signal alternates between the two. And that signal, if you take the Fourier transform of that in time, you will get the signal in the frequency domain. And you can see that there's a central frequency here, but the signal does occupy some bandwidth. And so that bandwidth is required in order to maintain the integrity of the signal. One of the issues with non-return to zero is that the different the different sequence of bits can result in different shapes of the signal. So if you have just a single one bit separated by zeros, that's a much narrower pulse compared to if you have a whole bunch of ones in sequence, which gives a broader pulse. Another modulation format is the return to zero signal, or RZ. With this one, all of the pulses have exactly the same shape because for every one bit, it starts from zero, goes to its peak, and then returns to zero at the end of the one bit. So it doesn't matter how many ones there are in a row, every one has exactly the same shape. And so if you overlap them with each other, you can see that all the one bits have the same shape. And if you take the Fourier transform, you can see that this is actually taking up a bit more um, width here in the bandwidth. Now, multiplexers work by taking all of these individual channels. So this would be one individual channel, and then you'd have another channel spaced out at a different central wavelength. So they take all of these signals and they combine them together to get this multiplexed signal as shown on the right, where this is a multiplexed non-return to zero optical spectrum with 1, 2, 3, 4, 5, 6 channels. So these channels need to be spaced close enough together so that you make efficient use of the bandwidth of the optical communication system, but far enough apart so that they're not overlapping with each other. Because if they are overlapping with each other in the spectral domain, then you will get leakage of one signal into the next, which is called a crosstalk penalty. So crosstalk penalty is if the wavelengths are too close together. There are other penalties that affect the bit error rate. Our goal is to minimize the bit error rate because you want to ensure the fidelity of the signal that is passed from its origin to its destination. You want to make sure that the right signal is achieved at the end. Other bad things that can happen are attenuation of the signal, which is loss of the signal due to scattering and absorption. There is noise that can be introduced through amplification, crosstalk, as I mentioned, different types of dispersion, and also optical nonlinearities, which reflects the change of the refractive index of the fiber at high intensities of light. Starting with attenuation, attenuation is typically expressed in units of decibels, dB, and decibels are 10 times the natural, or not the natural log, but the base 10 logarithm of the ratio of input power over output power. And so if you've got, greater loss of power, that would be a greater amount of attenuation. The bell would just be the logarithm of this ratio. Decibel is 10 times the logarithm. Modern optical fibers have attenuation less than 0.18 decibels per kilometer, which is really remarkable. But still, this means after 100 kilometers, there's 18 dBs of loss, so that requires amplification. Amplification is typically done with erbium-doped fiber amplifiers, or EDFAs. Erbium is a rare earth that allows for excitation of the electrons to an excited state. And with a stimulated emission of radiation, basically, these get excited to the higher energy state via a pump. So there's pump photons that go in at a higher frequency or lower wavelength that excites electrons to a higher energy state. And then when the signal that needs to be amplified comes in, that actually stimulates the excited photons to drop down to their ground state, emitting a new photon at exactly the same wavelength as the signal that came in. And so this stimulated emission of radiation in EDFAs allows for amplification of the signal. The downside is that it also produces noise because there's also spontaneous emission of radiation where the electrons relax from their excited state to the ground state on their own without being stimulated by an input signal. That spontaneous emission of radiation therefore produces noise. And so amplifiers are great because you can propagate the signal over longer distances by amplifying them, but the side product is that they do produce noise. Now, the next type of penalty is dispersion. There are three types of dispersion that we need to be concerned with. The first is the one that we already mentioned, which is the intermodal dispersion. This can be addressed by having graded index fibers or single mode fibers. Intermodal dispersion, as I mentioned before, is just because you can have different modes of light that take different amounts of time to propagate because of their different propagation distances, depending upon their angles. Chromatic dispersion results from the wavelength dependence of refractive index. If you've got different, any signal of any optical signal occupies a bandwidth of wavelengths, and within that bandwidth, the refractive index can be varying. So different parts of the signal could actually have different refractive indices and therefore propagate at different velocities and arrive at their destination at slightly different times. That's called chromatic dispersion. And the other problem is polarization mode dispersion. And this happens if there's if the core isn't perfectly circular in its cross section, but if it has any elliptical shape to it, then one polarization mode could propagate at a different velocity compared to another, and therefore arrive at different times. So polarization mode dispersion can be counteracted by having good process control during fiber manufacturing. Chromatic dispersion can be controlled by designing the fibers to have as flat of a refractive index profile as possible, or by using fibers that have the opposite dispersion compared to each other to cancel each other out. The last defect is optical nonlinearities. The optical Kerr effect shows that the refractive index of the glass is equal to its base refractive index, plus then some factor that depends on the power of light that gets passed in. So N2 is the nonlinear refractive index, P is the power of the signal, and that is spread out over an effective area of the fiber, P over effective area. Nonlinear effects come into play if you have very high optical powers. And what this means is that the refractive index can actually increase quite a bit at higher powers. And this can lead to a variety of penalties, including self-phase modulation, cross-phase modulation, and four-wave mixing. Let me show you an example of that, of four-wave mixing, where if you've got four different channels here that are all equally spaced, and let's suppose that three of them are at frequencies F1, F2, and F3. With four-wave mixing, the signal from each of these three different wavelengths could actually mix together to create a new signal at a fourth frequency, this four-wave mixing frequency here. And that new signal that's generated from the three other channels can fall on top of another already existing channel, and that can create a large distortion to that channel. And so nonlinear optical penalties like four-wave mixing really limit the amount of power that can be used in the signal. And that's what ultimately requires us to keep powers at a low enough level to avoid these problems and therefore use amplifiers then if the signal gets too low. All right, that does it for the course, everyone. Thank you so much for listening and following along. I hope you enjoyed it. I hope you learned a few things that will help stimulate your own research and help inspire the design of new glasses for new applications in the future. Please reach out anytime if you have any questions. It's been a pleasure having you in the course. Thanks, everyone.